Welcome to The Explainer. Let's just jump right in, shall we? Today, we're exploring a completely hidden, yet absolutely crucial layer of infrastructure that keeps aviation safe. We're talking about the invisible highways of the sky and an incredible new technology that's designed to make sure those highways are always pointing exactly where they should be.
Picture this for a second. How do military jets land safely when there's literally zero visibility? When the fog is so incredibly thick, a pilot can't even see the runway until their wheels are practically touching the tarmac? Well, the answer relies on highly precise, invisible radio frequency beams radiating up from the ground. But that really begs a much bigger question. Who exactly is checking those beams?
Think of a military runway kind of like a giant piano, and the navigational aids, or nav aids, are the strings. Naturally, over time, those strings go out of tune because of terrain shifts or just basic signal degradation. Right now, to keep these systems in perfect pitch, the Indian Air Force relies on a single, very rare, piano tuner aircraft. It's a manned Do-228 equipped with a Unifis 3000 system. They literally have to fly a whole entire plane just to measure these invisible beams.
Which brings us to the core concept here, nav aid calibration. Basically, this is the periodic airborne measurement of radio navigation signals to ensure they perfectly align with the physical runway. Without this super rigorous process, air margins start to drift, and pilots are essentially flying blind. These calibrations are what ensure systems like the Instrument Landing System, or ILS, actually meet strict operational standards.
Section 1. The Hidden Aviation Bottleneck.
So, as the Indian Air Force rapidly expands its military aerodrome and flying infrastructure, which is known as the Mafi network, relying on just one type of manned aircraft for this critical job has become a massive logistical nightmare. I mean, the contrast is pretty stark. The old way, using the Do-228, is really expensive, and the frequency of checks is completely limited by whether or not the aircraft is even available. If the plane isn't there, the calibration simply doesn't happen. The new way being proposed is the ADFS drone ecosystem. It entirely shifts the paradigm from periodic resource-constrained checks to continuous, autonomous, on-demand calibration.
Section 2. Enter the ADFIS drone.
And here is the absolute hero of our story, the Autonomous Distributed Flight Inspection System, or ADFS. This isn't just some minor upgrade. It's a total reimagining of national aviation infrastructure. Now, it's important to understand that the ADFS isn't just a basic drone with a radio strapped to the bottom of it. It's a completely decentralized system. It's a scalable, AI-driven national calibration grid that replaces one massive, single-point dependency with the distributed swarm of precision tools. It literally removes the human bottleneck entirely.
Section 3. The Flying Metrology Lab.
The engineering packed into this 15 to 25 kilogram carbon composite airframe is, honestly, nothing short of incredible. Just take the hybrid vertical takeoff and landing, or VTOL, architecture. It combines fixed-wing efficiency with VTOL flexibility, which gives it a massive 6 to 12-hour flight endurance. And every single component is engineered not as a drone accessory, but as a dedicated flying metrology instrument. Between the vibration isolation, the RF transparent radome, and the strict separation of noisy propulsion domains from ultra-clean radio payloads, it's built with the exact precision of a laboratory instrument. Let's trace the journey of a signal, because it happens incredibly fast. It hits the multiband antenna array, flows directly through low-noise amplifiers, and enters an analog-to-digital converter that's capturing over 100 million samples per second. From there, it hits an FPGA chip for real-time demodulation, and all of this is synchronized within 10 nanoseconds by a GPS-disciplined oscillator. So in just a fraction of a second, raw radio waves are transformed into actual, actionable data.
Section 4. The AI Calibration Brain.
But capturing the data? That's really only half the battle. Now we have to look at the software side, the 6-stage AI calibration pipeline. What this digital brain does is totally remarkable. It uses deep learning models to essentially reconstruct the full 3D radiation beam from just sparse samples collected by the drone up in the sky. And even more importantly, it uses Bayesian modeling to separate real terrain distortions, like signals bouncing off a mountain, from actual errors happening in the ground equipment itself. At the heart of all this math is a metric called difference in depth of modulation, or DDM. I'll keep the math pretty simple for us. Basically, the ground station transmits two overlapping tones, one at 90 Hz and one at 150 Hz. The exact invisible center line of the runway is the exact spot where the difference between these two tones is mathematically zero. The drone precisely maps this DDM, alongside DVOR phase differences, drawing what is essentially a perfect, invisible tightrope in the sky for jets to follow.
Section 5. built for the extremes.
Now, obviously, the Indian Air Force doesn't just operate on pristine, perfectly flat runways. Forward operational bases in mountainous terrains like Ladakh and the Northeast are incredibly rugged. And that is exactly where the old system truly fails. With the old Do-228 manned aircraft, these high-altitude, remote Mafi bases just couldn't be covered safely. The terrain is way too dangerous for a large plane to be flying erratic, low-level calibration patterns.
And that is exactly where this number comes in, 18,000 feet. The ADFIS drone boasts an absolutely incredible operational ceiling of 18,000 feet above mean sea level. This is made possible by a specialized turbocharged internal combustion engine paired with an electric hybrid propulsion system, all wrapped up in an anti-icing design. It can literally fly safely where manned calibration planes simply cannot go.
And since we're talking about a highly sensitive military asset here, it has to be able to survive in a contested environment. So the 85th features anti-jamming communications via frequency hopping, multi-constellation GNSS spoof detection, and AES-256 encrypted data links. If electronic warfare tries to scramble its brain, it just falls back on an inertial navigation system to complete the mission autonomously.
Section 6. The Future of Flight Safety. So, bringing all of this together, we're taking a fragile, highly aircraft-dependent periodic inspection process and turning it into an on-demand, fully scalable capability. And here is the bottom line, a greater than 60% cost reduction. By swapping out the Do-228 for an AI drone swarm, the cost of every single calibration mission is slashed by over 60%. At the exact same time, because you can now calibrate weekly, or hey, even daily, instead of just periodically, overall flight safety drastically increases.
Taking a system like this from pure concept to everyday reality takes a pretty ambitious 36-month roadmap. Months 0 to 6 focus heavily on lab validation. By month 18, a fully integrated prototype is actually built. Months 19 to 24 are then dedicated to intense flight trials against the old DO-228 benchmarks. And finally, months 25 to 36 secure airworthiness certification and final deployment readiness for the Air Force.
It's an absolutely brilliant leap forward in aerospace metrology, but honestly, it leaves us with one incredibly provocative thought to end on. If autonomous drones and AI can successfully tune the invisible highways of the sky to nanosecond precision, what other massive, hidden layers of our critical infrastructure will AI take over next? Thank you so much for joining me on this explainer. I hope it opened your eyes to the invisible forces guiding us safely home.